Okay, so I'm Jonghan Ri, Dingo project scientist. It's been a while since I gave an update on Dingo, so it's a good timing to bring you up to speed on Dingo today. So now I'm gonna tell you about what's been done and what's going on in the Dingo survey. So Dingo is an ASCAP deep survey to study H1 property of galaxy up to redshift 0.43. It has main science questions to answer, how H1 content of universe evolve, what the role of the H1 in the baryonic cycle of galaxies, how this changes with the environment and time, and what is the relationship between the angular momentum and H1 gas content. The original Dingo survey aims to observe 4 gamma fields with 7,500 hours in total. The extensive complementary data from gammas are essential to achieve the Dingo science goal that I just mentioned. Unfortunately, the recent review process outcomes for all ASCAP survey science projects allocated the Dingo the reduced time and the field for the full survey. Only 3,200 hours were granted, only for the gamma 23-hour field. Equally splitting the integration time to a 2 redshift range. And then before the full survey, we conducted early science and pilot survey. For Dingo early science, we observed a gamma 23-hour field using ASCAP 12 antenna. We divided the G23 field into 2 tiles. For each tile, ASCAP phase array feed receiver generated 2 interleave footprints of each 36 beam configuration, as you can see. This tiling strategy gives us uniform sensitivity across the field. So using the early science data, we conducted H1 spectral stacking analysis because the data was very too shallow to make many direct detection. However, this stacking experiment demonstrated the power of H1 stacking techniques, covering many science cases like this. After early science phase, ASCAP full 36 antenna array and with full bandwidth were available for full pilot survey observations. We observed the gamma 15 and gamma 23-hour field, while the GO9 field were observed as part of an ASCAP observatory project called SWAG-X, which is an eROSITA follow-up project. The main goals of the Dingo pilot survey were to obtain 100-hour data from one of the gamma tile to develop a Dingo the processing the pipeline for deep imaging and long-term data storage. And also to characterize the gamma equatorial field for the Dingo full survey, originally planned anyway, but and also test technical challenges of ASCAP data from equatorial field, which is such as the PSF artifact from that caused by these limited UV coverage. So the processing, the frequency range is for band 2, low redshift data, or only the higher half band due to the significant RFI impact below 1.3 gigahertz. The most of RFIs were sources were the GPS satellites, which are getting worse and worse in that frequency range. This is also a same situation for Meerkat. Anyways, the RMS of the process data sets are consistent with our expectation. So as I mentioned earlier, there is critical technical challenges in the equatorial field data. So some side lobe artifact from bright continuum sources, which is far away from the center, beam center, is the biggest problem for Dingo, as our observations are going deeper and deeper. So much fainter source can produce those artifact in the deep image, as you can see on the left-hand side, some images, which is a north and south artifacts. So we developed removable strategies, and then we demonstrated it works well. So we reprocess G15 data with this like a removal method applied. From the phase 1, the 50-hour G23 pilot data, we detected like about like 160 H1 sources below redshift 0.1. And the left figure shows the like a moment zero map of all detections color coded by the color. And the right hand one is the corresponding moment in one map. And then these detections are well above the H1 mass sensitivity limit, given the integration time and then current like ASCAP specification, as you can see in the this figure. And also, we also run like a source finding with the phase 2 data set. So 200 more detections were found in this from this phase 2 data set. This is due to the better optimized ASCAP imaging processing and then source finding parameters. Once source finding the processing has been completed, we will do like some direct detection science. So H1 detection represent like a relatively H1 rich population in the entire galaxy sample. However, H1 stacking technique like allow us to study overall H1 property of entire sample by measuring average H1 properties. As I said, we did like a stacking experiment with like an early science data set, but using the pilot data with the full ASCAP full array and then larger like a ancillary data set, we tried to reproduce like early science result and then conduct like a new stacking analysis. So all early science results are well reproduced with like the new data pilot data set. And then here I'm going to focus more on the like a new analysis result. So we are currently like comparing H1 gas content between AGN non-AGN population using Gamma AGN catalog, which is identify AGN by simultaneously like modeling AGN and host galaxy contribution to their SED using SED feeding code like a prospect. One of the previous like the study found like no difference like H1 content between AGN and non-AGN. As you can see in this, our like a global H1 content of AGN and non-AGN galaxies are very similar, but a little bit lower like H1 mass, but the similar H1 gas fraction. But however, when we look at the H1 scaling relation, we found that like a H1 and H1 gas fraction drop at high mass, around like a 10 to the 10 and 10 to the 10.5 solar mass, which is from which like AGN host galaxies are dominant below like a star formation main sequence, as you can see on the right hand star formation and then stellar mass like a domain. So for like a fair comparison, we divided the sample with the grid around the star formation main sequence, and then stack H1 for each grid samples of non-AGN and AGN respectively. So this shows the result of the this like a stacking. The column is like some offset from the star formation main sequence. Like a black one is like a little bit close to the star-bursting galaxy, and then blue one is the like a star formation main sequence, and red one is like a below like a star formation main sequence. And then different like a shape, like a square, it means like some non AGN galaxy, and then the star is like AGN galaxy, stuff like that. So this shows the AGN, the main sequence AGN has like a little bit lower H1 mass and the H1 lower gas fraction, as you can see in the box, the box in the middle. So it's between, especially between like a 10 to the 10 and 10 to the 10.5, which is like exactly the same range that we can see in the previous like the scaling relation. I think this is likely like contributed to the drop in the scaling relation. So and the other than like ASCAP, so we are also running like a follow-up observation campaign with the other telescope. FAST ASCAP Synergy project is one of them. So this project is aims to address like a discrepancy in H1 and halo mass relation between like interferometric data from DINGO and the single dish data set that we found in the early science paper. So we are going to directly compare different stacking method and then a halo mass estimation method using a homogeneous sample from both FAST and ASCAP. So we have allocated like a fast time to enough to observe one of the gamma field. So we observed like a gamma G15 field recently, so in the last month. So and then we will look into like some this kind of relation and also like a direct detection science with this data set. And then the other is the like a CO follow-up using APEX and ALMA called the DINGO and Co, led by Sambit Rohit-Choudhury. So H1 is closely linked to the like H2 because like H1 must be like converted to H2 for stars to form. However, the connection between like H1 and H2 and star appears weaker at the moment. So to gain a better understanding of gas fueling of galaxy and then constrain better H1 and H2 conversion, we are carrying on this kind of the H1 CO follow-up using APEX and ALMA compact array, as CO is used as like a proxy for H2 molecule in a galaxy. So, yep. And then DINGO is a good test bed technically contributing to the SKA.
You're just about out of time, so.
Yep. Anyway, so this is like some our technical stuff. So anyway, so and then this is a summary of our
there we go.
Things. Yep.
All right, let's thank Chung.
It's a bit challenging to give an update on DINGO within 10 minutes.